This is part 2 of a series on decision trees. In this video, we will look at the classification using ID3 and C4.5 decision trees. This video was produced in Korean and then translated into English. The voice was generated using text-to-speech. In the last video, we briefly looked at the history of decision trees and gave an overview of the ID3 and CART algorithms. In this video, we'll look at how to perform classification using ID3 decision trees. First, let's look at the concept of impurity and how to measure it using the Gini index and entropy. And let's look at the concept of information gain and how to split a decision tree using information gain. Now let's learn about impurity, entropy, and the Gini index. Let's consider 4 nodes, A, B, C, and D, as shown below. Node A has only 8 red data points, and node B has 7 blue data points and 1 red data point. Let's calculate the impurity of each node. Impurity can be measured by entropy or the Gini index. The formula for calculating entropy is as follows. Here C denotes the number of classes. In this case, there are 2 classes, red and blue. For example, let's say red is class 1 and blue is class 2. P denotes the probability that class I is included in a given node T. For example, node B has 7 blues out of 8 total data points. So this conditional probability is 7/8. And the formula for calculating the Gini index is as follows. This figure shows how the entropy and Gini index change as the probability P moves from 0 to 1. Entropy and Gini index are minimum when the probability is 0 and 1, and maximum when the probability is 0.5. The maximum value of entropy is 1, and for Gini index it is 0.5. That is, the impurity is maximized when red and blue data points are equally mixed at node T. These maximum values correspond to the case where the number of classes is 2. These values increase when the number of classes is greater than 2. We will discuss this later in the multi-class session. Now, let's calculate the entropy and Gini index of each node. First, let's calculate the entropy of node A. Entropy is calculated using this formula. The probability that I is red in this node is 8/8. The log value of this probability is as follows. And the probability that I is blue in this node is 0/8. The log value of this probability is as follows. Since 0 times log 0 can be defined as 0, the entropy of node A is 0. In this way, if we calculate the Gini index using this formula, that of node A will also be 0. This is the impurity of node A. Node A contains all the same color, so it has the lowest impurity, i.e. the highest purity. In the same way, the impurities of nodes B, C, and D are calculated as follows. Node A has the lowest impurity, and node C has the highest impurity. Since node C has an equal number of red and blue data points, it has the highest impurity. Impurity is a measure of the average amount of information or uncertainty in a system. In information theory, higher impurity means more uncertainty and more information, while lower impurity means less uncertainty and less information. In this case, node C has the highest amount of information and the highest degree of uncertainty. Next, let's look at the information gain. Information gain is a measure of the expected reduction in impurity after a node is split. Let's consider the two nodes A and B below. Let's split each node into a left child node and a right child node as follows. The capital P denotes the parent node, and L and R denote the left and right child nodes, respectively. We will use the Gini index to measure impurity. First, let's calculate the Gini index of the parent node. This node contains only red data points, so its Gini index is 0. We use this split point to split the parent node into two child nodes. The left child node contains 5 red data points, and the right child node contains 3 data points. The Gini indices of the child nodes are all 0. Let's calculate the amount of information gain due to the split of node A. The formula for calculating information gain is as follows. Compute the difference between the Gini index of the parent node and the weighted average Gini index of the two child nodes. The first term is the amount of information the parent node has before splitting the node. And the second and third terms are the amount of information the child nodes have after splitting. If this value is greater than 0, the parent node's impurity is high, while the child node's impurity is low. In other words, the split results in information gain. Let's calculate the information gain when splitting node A. The Gini index of node A before splitting is 0, and the Gini index of each child node after splitting is also 0. Therefore, the information gain is 0. An information gain of 0 means that the split does not reduce impurity. That is, this node does not need to be split into child nodes at this split point. Node A has all the same class, and its impurity is already at its minimum, so it cannot be reduced any further. This time, let's consider the case of node B. Since the parent node contains 4 reds and 3 blues, the Gini index is 0.49. Let's split this node into 2 child nodes at this split point. The left child node has only 3 reds, so its Gini index is 0, and the right child node has 3 blues and 1 red, so its Gini index is 0.375. Let's calculate the information gain in this case. If we subtract the weighted average Gini index of the child nodes from the Gini index of the parent node, we get 0.278. This is greater than 0. This means that this split yields information gain. That means it's beneficial to split the node B in this way. By using information gain in this way, we can determine whether it is better to split a node at a certain split point or not. This allows us to build an optimal decision tree that minimizes impurities at each split. Next, we'll look at how to build an ID3 or C4.5 decision tree using information gain. Let's use the dataset below. This dataset has 2 features and 1 target class. The target class consists of 0 and 1. This is part of the Titanic dataset. Let's plot these data points in a 2-dimensional space with axes p-class and sex as follows. When building an ID3 decision tree using this dataset, we have 2 choices. The first choice is to split the feature p-class first, and then split the feature sex. The second choice is to split the feature sex first, and then split the feature p-class. Using information gain, we can determine which of the 2 is the better choice. This time, let's calculate the information gain using entropy. The figure above is the root node. Let's calculate the entropy of this node. Of the 18 total data points, 8 are blues, and 10 are reds. Then the entropy of the root node is 0.991. Next, let's calculate the entropy of the child nodes when splitting the feature p-class. The first child node with the feature p-class of 1 has 4 blue data points and 2 red data points out of a total of 6 data points. Then the entropy of this node is 0.918. If we calculate the entropy of the other child nodes in the same way, we get 0.971 and 0.863 respectively. And if we calculate the weighted average of these entropies, it is 0.911. Next, let's calculate the entropy of the child nodes when splitting the feature sex. The first child node with the feature sex of male has 4 blue data points and 7 red data points out of a total of 11 data points. Then the entropy of this node is 0.946. In the same way, if we calculate the entropy of the child node whose sex is female, we get 0.985. And if we calculate the weighted average of these entropies, it is 0.961. Next, let's use these entropies to calculate the information gain. The information gain of p-class can be obtained by subtracting the weighted average entropy of the feature p-class from the entropy of the root node. The result is 0.08. If we calculate the information gain of sex in the same way, we get 0.03. Comparing these two, p-class has greater information gain. This means that it is better to split the feature p-class first. That means of the 2 trees above, the first one is better. By using information gain in this way, we can create an optimal ID3 decision tree. Then we can create an ID3 decision tree like this for this dataset. First, split the feature P class, then split the feature sex. This is the optimal tree with minimum impurity. Next, let's use this tree to predict the class of this test data point. P class is 3 and sex is male. This belongs to the right child node of the root node and the left child node of this node. Then this test data point will belong to the fifth leaf node. Since this node has more red, the class of this test data point is predicted to be 0, which is red. Next, let's look at a dataset with continuous real values. A continuous feature, age, has been added to the previous dataset. This feature has continuous real values. To split this feature in multi-way, we converted it into a categorical feature as follows. This can be done by dividing the data points into bins, or intervals, based on specific percentile ranges. In this example, the ages are converted to percentile ranks and assigned to 4 bins with nearly the same number of data points in each bin. The data points with ages less than 24 are assigned to bin 1, and the data points with ages greater than 36.75 are assigned to bin 4. Now let's calculate the information gain of the converted age. Let's calculate the entropy of the node whose age prime is 1. This node contains the following 4 data points. This node has 3 data points with target 0 and 1 data point with target 1. So the entropy is 0.811. Calculating the entropy of other sibling nodes in this way yields the following results. If we calculate the weighted average of these entropies, we get 0.9. In the previous slide, the entropy of the root node was 0.991. Therefore, the information gain of age prime is 0.091. This is greater than the information gain of other features. Therefore, it would be best to first split this dataset by the feature age. Next, we split the P-class feature and then the sex feature. In this video, we looked at how to calculate impurity and information gain using the Gini index and entropy. And we looked at how to create an ID3 decision tree using the information gain. In the next video, we'll look at the information gain ratio and tree pruning. We'll also briefly implement an ID3 classification model.